Warning: tube amplifiers have lethal voltages inside them. Please do not attempt to build, test, or repair these without understanding and following all safety protocols. Hey y'all! Well, we're getting close to having this thing finished. As you can see, it all looks pretty nice. And the little screws back here, you really can't see from the front, so I'm not too concerned about that. It may end up trying something later if it really bothers me, but I think when it's sitting on the shelf, it's not going to be an issue. So, ready to wire up the input tube phase splitter and get that connected to the RCA jack volume control and the output tubes, and then power it up, run some voltages, and then put it on the scope. So I think we can do all of that in this episode. So let's get busy. Okay, so I want to show you how I'm wiring up this input tube and phase splitter. This dual triode is being used for both of those functions. This section on this triode is being used as the amplifier or the driver tube, and then this side over here is being used as our phase splitter. And so what we've got wired up so far is I've got this 124K resistor that's going from the cathode over here to the ground. This similar terminal has got a ground that's running over to our star ground point. It also has a ground lead that runs from here up to this side of the potentiometer. Our signal comes in on this side of the potentiometer, and then we pull the feed that goes to the grid of the driver tube off the center of this potentiometer. Now, when this potentiometer is working like it's supposed to, the resistance between the center pin and the ground act as our grid leak resistor. But I like adding a 1 meg resistor across from the center point to the ground as a safety in case something happens to this potentiometer and the wiper loses connection with the ground, that the tube always has the grid reference to ground through this 1 meg one to ground. But like I said, majority of the time it's going to be using the wiper inside the potentiometer as the ground reference or the grid leak resistance. We're going to tie these two terminals together and run them over to our B+, which I'll show you in a second where it's being wired up. So we're going to have a resistor that runs from this positive terminal down to the plate of the phase splitter, which is another 24K resistor. Now it is important that you try to match these 24K resistors as close as you can, and I had about 6 of them that I went through and found pairs of them that are matched really close. So get that soldered in place, and we'll have a 24K on the cathode, a 24K on the plate. We've got this 100 ohm resistor that comes off of the plate of the amplification triode over to the grid of the phase splitter. And that's the only thing that's hooked up to the grid here is this 100 ohm resistor. Then we're going to hook up a 75K resistor. It's a 3 watt one that goes between this terminal and the plate of this amplification triode. Again, the grid's hooked up to the potentiometer. The cathode, I'm going to run just a straight wire over to this pin on the far end here. We're going to put the 100 ohm resistor between here and here. And then there's a 220 ohm resistor and a bypass cap that are going to run from this terminal to ground. Then when we get ready to run our feedback circuit, or the negative feedback, I'm going to come off of this speaker jack and just run it over here to this terminal, which will then go over to the cathode of the amplifier tube. So I think that's going to be about as neat as I can make this. So let me scoot this over and show you some of the other wiring. So these are the two output tubes, and you can see we have the blue wire for the transformer hooked up to this one and the brown to this one. When I'm at this stage looking at all of this, I wish I had wired these up the other way. It's not a big deal, but if I was doing it over again, I would have this be the brown and this be the blue, because looking at the ED core schematic of the transformer that looks like this. You can see the brown wire is down at the negative side of the output and the blue wire is up at the positive side. Now I'm assuming that that means that I need to put the positive signal to this output tube and then the negative signal to this output tube, which means the leads for the coupling caps are going to have to cross each other because this is the grid of the output tube and this is the grid of the other output tube where the signal goes. So we're going to be hooking this terminal, which is the positive half of the amplification, to this terminal of the phase splitter, and then this will be the negative of the phase splitter that's going to hook up to this tube over here. Now again, first time I've built a push-pull amp, and I'm assuming that's how it works. If we get this wired backwards, then when we go to apply the negative feedback from the output around the whole amp back to the input tube, the amp will just scream. And if that happens, then I'll just have to reverse these two leads on which output tube is fed from which pin of the phase inverter to get everything back in phase so that the negative feedback works correctly. And again, I'll show you from this angle. It's probably a little easier to see how some of these pins are oriented. This tube is going to be the B plus that comes over from here. It's going to be a wire that goes from here to here. And then this is going to connect with a 24K resistor to here. Then this one, which these two are tied together, this one will have a 75K resistor, the 3-watt one that comes over here to the plate of this tube. And then we have the cathode of the input tube coming to this pin, 100 ohm across to this one, then a 220 ohm across this with a capacitor across those two. And then we'll be running the positive signal off the phase splitter over to this pin, and then we'll be running the negative signal from this one over to the grid of this other tube. Now here we have a little decoupling network between the output tube power supply and the input tube power supply. This wire comes from our B plus storage cap, goes through a 1.5K resistor, and then there's a 47 UF 450 volt cap that goes from this positive to ground that acts as the filter for the input tube power supply. And then again we'll run the positive from here over to our tag strip for the input tube phase splitter. And the last thing, and this ended up being a little uglier than I would have liked, we have these two pins are our heaters. We had to create a virtual center tap. So we had a voltage divider here that creates 50 volts on this pin here. So then we had to run a 100 ohm resistor over to this pin, and then another 100 ohm resistor from here over here. And this ended up being a little more messy than I would have liked, but when you're retrofitting something that's already been half soldered together, sometimes it just ends up not being the neatest thing that you'd ever want to see, but it will be functional. So anyway, I'm going to get back to wiring all of this up, and then before I hook up the coupling caps from this phase splitter to the output tubes, I'm going to power the amp back up and check all the voltages on the different pins and make sure this stuff looks reasonable. The schematic that I'm working off of doesn't really have any voltages on it for like what these are supposed to be. So I'm going to have to look at what the tube data sheets show me as being the maximums and those kind of things, and make sure the dissipation off of the cathodes of both of these look reasonable and we're not overworking these tubes. And we'll get to that in the next segment of this video. So let me get to soldering here, and I'll be back in a few. Okay, I got the rest of these resistors installed. 75K, the 24K. Got these two 100 100 ohm, 220 ohm that are going over here to the cathode. And then we have this bypass cap here. And I am putting audio note caps inside this thing. Some of their lower end ones, not the super expensive ones, but they're not a whole lot more than regular caps. And in my opinion, using caps like this, you don't have to worry about bypassing them with film caps or something like that, trying to get good performance out of them. They're ready to go just, by themselves. So anyway, the schematic that I have that I'm working off of really doesn't show any of these voltages or what they're supposed to be. And so I'm just looking to make sure that things don't look wacky and, they're kind of what I'm expecting. So anyway, without further ado, let's power this thing up and see what these voltages look like. And like on the other power-ups, it goes up to almost 400 volts and then it comes down. That's why we're using 450 volt caps, even though the amp's not running at those voltages. We know that it's going to be seeing, like over 350 volts. So 450 volt caps are a safe bet for all these power supply caps. So there's, looks like 322 on the B plus after the 1.5K resistor coming over here to the input slash phase inverter. Let's see what we have on the plate of the input tube. 115 volts. That's clearly not going to melt anything. The cathode, we have just under 1 volt. So that should be the bias for the input tube. So that sounds reasonable to me. Let's go over here and see what the plate on the phase inverter is, or the phase splitter. Got a little over 200 volts. And on the cathode, we have 115. And this 115 voltage on the cathode of the phase splitter is why we had to lift the DC offset on the heaters to make sure we didn't exceed the maximum, which on most of these tubes is 100 volts. So we're kind of splitting the rating between these, like on this other part of the tube, we've got like 1 volt, which is almost, 0 volts. But then over here, we got 115 volts. So having 50 volts on the heater keeps both of those safely within their 100 volt spec that they're allowed. And then this will be the grid of the phase splitter. So we have 113.8. And we'll look at this one again. It's 114.3. So we have a little bit less than 1 volt of bias on the phase splitter grid. So that all sounds reasonable. So I think now I'm ready to go ahead and run the, let me turn this off. I'm ready to run the coupling capacitors across, from here to there, from here to there, and get this thing wired up, ready to hook up a signal generator to it and put a scope on the output and see what this thing does. So let me go put these coupling caps in and get this thing, get my bench cleaned up a little bit and get this thing hooked up to the signal generator and see what this thing does. Okay, so we got the amp all assembled and we're ready to do our first round of testing. I always do my first round on my old Tektronix oscilloscope and using my Tenma audio signal generator. This generator has this knob here that changes the frequency. You can change the output here. This switches between square wave and sine wave, and then these are the different ranges of frequencies you can select. So you can see here I have a probe hooked up to the positive and the ground of our signal generator that goes to channel 1. Channel 2 is hooked up to the positive and the negative with an 8 ohm load on the output of the amplifier. You always want to have a load on a tube amp when you're going to be running them, especially if you're running a signal through them. And you can see here the signal generator comes in here to the RCA jack, and then here is the amplifier, and then way over there, the little black box is the isolation transformer that isolates the device under test from the ground of the oscilloscope, because you never want to have them sharing the ground just in case there's something weird going on. So, and you always want to have the oscilloscope grounded. One thing a lot of people don't understand on a scope is these outside of the B and C connectors are hooked to the house ground circuit. And so you want to make sure that you don't have some kind of a weird problem going on with the ground on the amp and the ground on the oscilloscope. And using an isolation transformer just keeps everything safe and avoids something that might end up smoking your signal generator. So anyway, just wanted to show you my setup here, and let's get ready to test this thing and see what the initial test looks like. Okay, we're seeing the wave pattern here of the signal generator, and we have a 200 hertz signal coming in with 3 volts peak to peak. We have this set on 1 volt divisions, and so that's 3 volts. And we got the amp warming up. We've got this set on 2 volts per division for the output of the amplifier. And let's do the first pull here and see what this waveform looks like. Wow, that is ugly. It's all out of phase. See how it's shifted from what's coming in, and it's super freaking distorted. See how peaky that is? It doesn't look anything like the signal coming in. And let's see, let's go ahead and switch this to 5 volts. And wow, that is ugly. Guys, I don't know what's going on. Let me switch over to the square wave and see what. So there's our square wave coming in, and that is not good. This is showing me that only high frequency stuff's being amplified, and nothing on the lower frequencies is being amplified at all. I'm not sure what's going on here. Let me try switching to 2000 hertz and see what the sine wave looks like there. Okay, that looks a little better, but man, it's clipping at super low power and asymmetrically clipping. But does seem to be doing better at higher frequencies. Let's see what the square wave looks like. Okay, it's still all jacked up. See how it's super angled like this, which is showing me it's not able to amplify the low frequencies like it is the high frequencies, but it's better. So that's giving me a little clue there. Let me go ahead and turn this up to 8K. Go back to our sine wave, and It's still clipping at low power, but the waveform seems more symmetrical. Well, not symmetrical, but it doesn't look as distorted. It looks more even, following the pattern of what's coming in. And now the square wave seems to be able to handle the whole range at this frequency of square wave. Clearly there's something wrong. This amp cannot be this bad. Too many people have said that this amp sounds good, and there is no way that this is going to sound good at all with this scope output. And I don't know what's going on. I'm going to have to go back through and look at the amp and try to figure out if I've got something wired wrong or there's a wrong component or something. Clearly it's acting like there's a high pass filter in place, which obviously we don't have one in it, but something's wrong and it's not letting the low frequency signal go through the amp for some reason. And again, this amp may not be the be-all end-all of audiophile goodness, but this is horrible. And I know this would sound like garbage if I tried to listen to it, which I'm not going to even do. So, anyway, this is the reason why we do this test on a scope first before we hook up any speakers or do anything else, is to weed out problems and make sure that everything's working like it should. And clearly it's not. So let me dive into this thing and see what's going on and see what I can find wrong. Clearly something is amiss. Sadly, I don't have voltages on the schematic to know if everything's working right on the input tube and the phase splitter. And it might take me a minute or two to kind of wrap my head around what may be going on and figure out what's happening with this thing, but I'm sure we can figure it out. Well, clearly that isn't the results we like seeing on a test, but again, a lot of this is a learning experience, and I'm sure there's a good reason that we got the results we saw. I don't know if I've wired something wrong. I gave it kind of a quick look through compared to the schematic, and it looks like all the pins are going to the right places. But again, I need to dive into this thing and try to figure out what's going on. We do have some clues in that it appears that no low frequencies are going from the input jack to the output jack. So there's something inside the circuit between the RCA jack and the output transformer in output jacks that is acting like a high pass filter. So that's a good clue to me that there's probably something going on with I don't know if a capacitor or something. I just don't know. And I mean, I made a couple of small tweaks to the power supply and stuff. But I can't see that doing that. Again, I don't have a lot of experience with push-pull amps, and so if any of y'all want to take a guess, you can put it in the comments, and then you can see when I figure out what's going on whether you were right or not, and maybe help me kind of lead me in that direction. I'm going to try to dive into that later tonight, and over the weekend I should make a follow-up video, hopefully with the solution to this problem, and have this thing singing like it should be. I do know that we're probably going to be tinkering around with the feedback some, given I'm using this EdCore output transformer instead of the Dyna, which a lot of other people are using. I'm also now going to figure out how to paint these black to match this. I just think this blue looks funny now. I mean, I do have another amp that has blue output transformers with a black power transformer and choke, and I've lived with it, so I don't know. I think this one I'm going to paint black. But like I said, this is why I have an oscilloscope and why I run these tests before I ever put these in a system or hook these up to speakers to see if there's something crazy going on. And clearly we've got crazy going on, but we will figure this out. Anyway, hope you're enjoying this series. If you are, please subscribe, please like the video, and we'll see you soon. Have a great day.